Morning student. In the last class we discussed about the torque on a current carrying loop in a uniform magnetic field, and we considered two conditions when the area vector a cap is perpendicular to the magnetic field or area vector a cap parallel to the magnetic field. Okay, parallel or anti-parallel to the magnetic field, that is phi was equal to 90 degree and phi is equal to 0 or 180 degree, right? So we found that for phi is equal to 90 degree, the torque acting on the loop was tau is equal to I A into B into capital B into J cap, or plus minus J cap depending on the direction of the current. And for phi is equal to 0 degree or 180 degree, we have found that tau is equal to 0. So at this position the torque, the current carrying loop does not rotate at all, but at phi is equal to 90 degree the torque was found to be maximum. Okay, now what we are going to do, we are going to do the calculation for phi is any arbitrary angle. Okay, that means the area vector a cap and magnetic field B, they are at any arbitrary angle. In the earlier case, as you remember, suppose this is a uniform magnetic field, B magnetic field in the say x direction, and the current carrying loop was, this is x, say this is y, and this is z direction, and the current carrying loop was in the xy plane. So the normal vector to that current carrying loop was along the z direction, say positive z direction. So in this case the phi and the angle between the magnetic field and the current carrying loop was 90 degree. Okay, and also we discussed the condition when magnetic field, and suppose this is the direction of the magnetic field, say this is in the z direction, and the current carrying loop was in the xy plane. This is x, this is y, therefore the area vector was also along the direction of the magnetic field. So in that case phi is equal to 0 degree, or if it is the orientation of the magnetic field is opposite, then phi was equal to 180 degree. Okay, so for these two cases we have already done the calculation. Now what we are going to do for phi is any angle, say 20 degree, 45 degree, it can be anything, any angle. Okay, so that part of the problem we are going to solve, and we can prove that for this when this arbitrary angle become 90 degree, then we will get this expression, and when this arbitrary angle is 0 or 180 degree, then we will get this kind of expression. So that part of the calculation we are going to do. Okay. Now let's consider in this figure, suppose ABCD is the current carrying conductor. Suppose current is flowing along this direction. Okay, ABCD is the current carrying conductor. Now this line is the initial position of the current loop, and suppose now we have slightly rotated the current loop. Okay, so its final position become like this. Say now the current loop position is A, B, C, D. Okay, it's shown by the dotted line. Okay, so whatever the normal vector when this current loop was in the xy plane, then it will also now changes, because you know, suppose this is a, suppose this line, it's easy to show in two dimension. Suppose if this is a line, then normal to this line will be here, and if the line is tilted to this direction, the normal will be this direction. Okay, so this similar type of situation happens here, only the difference is that this is two dimension and this is in a plane, therefore it's a 3D case. So in this case also similar to the two-dimensional case, the normal vector will changes. Okay, and we hope that and we assume that the normal vector to this line, the line CD, the dotted line, is now along this direction. This is the A cap, our area vector. Okay, so this is the value of the A cap, and therefore on the line AB also, say this is the value of the area vector and A cap. Okay, and the angle between the area vector and magnetic field, say this is equal to phi. Okay, So this angle is equal to phi. So this is the angle between the area vector and the value of the magnetic field. Magnetic field is shown by the red line. Okay, magnetic field is say all in the x direction. Okay, it is shown by the red line here. Okay, now current I is flowing along this loop. Same current I is also flowing in this loop. Okay, I current is flowing in this loop, and now we are going to determine what is the value of the forces on the arm CD, AB, BC, AB and AD, and after that we are going to see whether there exists any torque on this rectangular current loop or not. Okay, as earlier, the length of the current loop is B and the breadth of the current loop is A, which I have considered in the earlier case also. Okay. Okay, you see breadth is B and the length of the current loop is A in the earlier case. So in this case also we have considered the same thing. Okay, so this is B, sorry, and this is A. Length of the current loop is A and breadth of the current loop is B. Okay, now what we are going to see, what are the forces acting on the current carrying element. Okay, this force, the force on the current carrying element CD, we have termed it as F1. So F1 is on the line CD, and this force I think we have termed it as F3. Say F3 is equal to AB. You can do at your choice, it doesn't matter. And say F2 is on BC and F4 is on AD. Okay, you can choose. I mean, it doesn't matter. Only the final outcome will matter. Okay, so we are going to find out this value F1, F2, F3 and F4. Okay, now let's concentrate on the line element CD. The length of the line element is B and current is flowing along this direction. Okay, and now the area vector is making an angle phi with the B vector. Now we are going to find out what is the value of the angle between the current carrying vector and the magnetic field. Okay, so you see this is the direction of I, therefore DL will be along this direction. Okay, and B is along this direction, therefore the angle between the current element and the magnetic field will be this angle. Okay, so we have to find out the value of this angle. Okay, now since A cap is normal to the line AD, because A cap is a normal vector, therefore it has to be perpendicular on the line AD. Therefore this angle, as you can see in the figure, this angle, this total angle will be equal to 90 degree and this angle equal to phi. Therefore this angle, the angle between the magnetic field, say this angle will be equal to 90 minus phi. Okay, so for F1 we know that the angle between L length and magnetic field B is equal to how much? It is 90 minus phi. Okay, I hope it is clear, because you see on the line CD, A vector is perpendicular, so this angle is 90 degree, and the angle between B and A cap is phi, therefore this angle will be equal to this angle will be equal to 90 minus phi. Okay, so now we are going to calculate the value of this force. Say F1 is equal to I into L cross B vector. Okay, this will be equal to ILB, the angle between L and B. L in this case is nothing but the breadth of the current loop. So this will be the angle will be 90 minus phi. Okay, the magnitude of the force. So IAB sine 90 minus phi is equal to cos phi. Therefore F1 will be equal to IAB into cos phi. Okay, so this is the value of the angle we have found. Okay, now let's find the force acting on the line AB. Say this is the line AB, and what is the force acting on the line AB? Okay, as you can see, the current is along B to A. Therefore here the length vector will be along this direction. Okay, and magnetic field is along this direction. Okay, so what we have to find? We have to find out the value of this angle. So what we have to find? We have to find out the value of this angle. This angle we have to find out the value. Okay, so this is the direction of L and this is the direction of B. So basically we have to find out the value of this angle. Okay, also we know that area vector is along this direction, therefore the angle between the area vector and this line element, that is DL, this angle is equal to 90 degree and this angle is equal to phi. Therefore this total angle will be equal to sum of these two angles, so phi plus 90 degree. Okay, so I repeat it again. What we have to find? We have to find the angle between the length element and the magnetic field. So basically what we have to find? We have to find this angle. Okay, and we know that area vector makes an angle phi with x-axis and and this angle, the angle between the area vector and the length element is equal to 90 degree. So basically this angle will be equal to 90 plus phi. Okay, so the force F3 in this case will be equal to F3 will be equal to I L cross B. Okay, so this value will be equal to I L B sine 90 plus phi, because now the angle between length and the magnetic field vector will be equal to 90 plus phi. Sine 90 plus phi will be equal to cos phi basically. So this value will be equal to I L B cos phi. Again this value will be equal to I L B cos phi. Okay, now we have to find out the direction of the force which acting on the line element CD and AB. Okay, so this we can determine from the right hand thumb rule. If you curl your finger from L to B, then the direction of thumb will give you the direction of the force here. So in this case, the force acting on the line element CD, if you apply the right hand thumb rule, you will find that this force is along this direction, and the force acting on the line AB, it will be along this direction. So if it is F1, then F1 will be along this direction and F2 will be along so F3 will be along this direction. Okay, now if you see the line of action of the force F1 and F3, the force is equal and opposite, but their line of action will be same. Okay, so if you just join a line, then the force will be at the two ends of this line. So that's why we term these forces as the coplanar forces. I think you have already found in the last example, in the last derivation, the example of the coplanar forces. In this case, the force F3 and F1 will also be a coplanar forces. Okay, therefore the coplanar force, they does not generate any kind of torque. Okay, so the torque due to the force F1 and F2, so if we write the net torque due to the force F1 plus F3, this will be equal to 0. Therefore this torque will not act on the current loop at all. Okay, so we found that the force F1 and F2, although their value is equal and their direction is opposite, therefore they will totally cancel out each other. So F net is also 0. F net is 0 in for these two arms, but tau net is also 0 because these two forces are coplanar forces and the coplanar forces does not constitute any kind of a current. Okay, so we found that for CD and AB, that forces does not contribute to any net torque on the current carrying loop. Okay, so now what we are going to consider, we are going to consider what is the force on the line AB and BC. Okay, AB current direction is this and BC current direction is this, and magnetic field direction is perpendicular to both the lines. Okay, so if we consider the current I is along the y direction, therefore the length L will be in this case, length L will be along y direction. So we can write A into J cap. Okay, and for the arm AD. And what is the force on AD? The force on AD is F4. So for force F4, we know L is equal to A plus J. Okay, and magnetic field B is equal to, how much is the value of B? B is in the direction of I cap. Okay, so I into F4 will be equal to I into L cross B. Okay, so this value will be equal to I A J cross B into I cap. So this will be equal to minus I A capital B K cap. Okay, so this force will be in the negative Z direction. So minus IA, minus symbol represent the forces into the plane of paper. That means in the negative Z direction. If I orient the force, if I show this force on the line itself, then this force will be into the plane of paper. That is, it's into the in negative X direction. So this force is along this direction. Okay, now again, if we consider the force on the line BC, then this force is equal to F2. Okay, and for this segment, BC segment, you see the current is along negative Y direction. Therefore, length vector L is equal to minus A into, this is for force on BC is F2. So this calculation is valid for F2. L is equal to how much? Minus A into J cap, that we know. And magnetic field is always in the X direction. So B into I cap. Therefore, F2 will be equal to I into minus A into J cap plus B into I cap. Okay, and J cross I is equal to minus K, minus plus. So it will be I A B into K cap. Okay, so you see F2 is equal to IB into KK. This is positive value, therefore the force will be out of the plane of paper. So if I write if I represent the force on the line segment itself, so this force will be outside of the plane of paper. Okay, so for AD, the force we have found into the plane of paper, and its value is IAB minus, and for CD, the force we have found to be outside of the plane of paper, and its value will be IAB. Okay, now you see all these two forces are equal and opposite, because they are, you can see these are one is positive X direction and positive Z direction, and another is minus negative Z direction. But the thing is that their line of action will not be equal. For example, if we say this is the distance between the 2 points which we considered here. So if this is a point, say P, and this is a point Q, then one force will be, if one force is along this direction, and another force will be along that direction. Okay, so from this these two forces, they will try to produce a torque, and that torque will be responsible for rotation of the current loop in its plane. Okay, so we found that if the loop is placed in at an arbitrary angle, then the force on CD and AB will be equal and opposite. They are these two forces will be coplanar, therefore they will not constitute towards any net torque. But on the other hand, the force on AD and BC, they are also equal and opposite, therefore net force is 0. But in this case, the force is not coplanar. As you can find from this figure, these forces will be will have different point of action, therefore they will constitute a torque, and that torque is basically going to rotate the current loop in its plane. Okay, so in the next part, I am going to find out the magnitude of this torque.